RF Man here. This will be part 2 of my video series on RF transformers. I apologize, this has taken me several months to complete due to other priorities and other projects, but I finally got this done. This particular segment is going to focus on conventional RF transformers. So let me explain what I mean by that. Here, if you recall, in part 1, we talked about a transmission line transformer. Here we're talking about a conventional RF transformer, the type that we would use in an RF amplifier, whether bipolar or LD-MOS. So basically we're talking about transformers like this, where we construct them with ferrites and copper tubing and some PCB end plates. That's one type there that's wound with Teflon wire. And here's another type that I have. Okay, this is also a conventional transformer. It's just wound with coax. This should not be confused with the TLT transformer, which is this type, which is also wound in coax. So this particular transformer just has a primary and a secondary like you see here. And the TLT transformer is basically an auto transformer with a combination of series and parallel windings. And we'll cover this one in part 3. So let's go back to the conventional RF transformer. Pretty basic. You have a primary and a secondary. You have the number of turns in the primary, which in this case, this example is 1, and number of turns in the secondary, which is 3. So we call this a 3-to-1 because you're looking at the ratio looking into the transformer in this direction. So primary and secondary windings are coupled through electromagnetic induction and provide galvanic isolation between the primary and the secondary, as opposed to an auto transformer or TLT transformer where we need to use blocking capacitors. And we'll talk more about that in part 3. So it provides total, complete isolation here, and it follows transformer theory. So basically we look at the ratio of the secondary turns and primary turns, and we take the primary voltage, which in this case is 100 volts, and we divide basically 1 divided by 3 is 3, so we get 100 times 3 or 300 volts on the output. And more importantly, the RF transformer also is used for impedance transformation to match the impedance from a primary side to the secondary side, or typically where we have low impedance, which is the output impedance of the transistor, to high impedance, which would be the 50 ohm impedance of our antenna system or our load. So we all should know this from my previous videos, that the impedance ratio is the turns ratio squared. So basically, if the turns ratio is 3, 3 squared equals 9. So that's just a basic overview. Here's the topics that we'll be covering. The main topics would be understanding ferrite core specifications, how to select the right core and core size, understanding the turns ratio and impedance ratio. We'll go into a little more detail about that. Determining the primary and secondary inductance. There are minimum values that need to be considered. Evaluating a transformer model and SPICE simulation. And then one of the more important areas is measuring the insertion loss of the RF transformer with a NanoVNA, and then how we actually tune the transformer. So those are the main topics that we'll be addressing. So let's first talk about ferrite materials. When you look at the different ferrite materials for the HF band, we typically use material 43 or 28. They're very, very similar, or material 61. We're going to answer some questions about why. So typically material 43 and 28 is used for TLT transformers and splitters and combiners, and material 61 is used for the output transformer where our power levels are fairly high. The primary reason we use material 61, it has a much higher saturation point, and we'll show you some of those calculations. So the areas we'll be looking at is what is permeability, what is the operating frequency. That's typically included in the text or might be in the table. So you can see for 4328, it's 20 megahertz to 250, and for 61, it's up to 30 megahertz for inductive applications, and 200 for EMI suppression. So we'll be looking at the operating frequency, the Curie temperature, the flux density, and the saturation point. So those are the most important parameters on these tables and in the data sheets that you'll find. So here's permeability versus frequency. So this is material 61 here, and you can see it's rated for inductive applications up to 30 megahertz, and you can see that the permeability drops off above 30 megahertz. It drops off, it's a fairly sharp drop off. Okay, and here we're showing material 61 versus the Curie temperature. Now this particular material, the Curie temperature is extremely high, so we typically don't worry about that. But if I go back to material 43, the Curie temperature is rather low, 130 degrees C compared to 350 degrees C. So you can see again that this is where you can actually alter the properties of the ferrite material permanently. It can be damaged. You affect the magnetic structure, and the permeability drops off very quickly. So that's how the ferrite material responds with temperature and frequency. So what's important about permeability is the higher the permeability, the higher the inductance is per turn, and vice versa. The lower the permeability, the lower the inductance is. So here's the ferrite core that we're going to be discussing. This particular core is very popular in the transformer I just showed, material 61. It's from ferrite. Some of us recognize that. And it's material 61. Here are the dimensions here, nominal dimensions. We'll talk in English instead of millimeters. So 1.0 is the diameter, the outer diameter. 0.5 is the inner diameter. And then C is the overall length, 1.1 inches, we'll call it. So this is the typical ferrites that we use, and there's the Gauss that we'll be talking about in a moment. So guidelines to select the right core, the right size, the right type. So we need to understand what the cross-sectional area of the ferrite material is. We typically call that AE. And there's, of course, different shapes of ferrites. We have a toroid like this one. We have ferrite rods. Okay, so you're going to have different shapes to consider. In this case, the ferrite core that I showed in my transformer is a rectangle. It approximates to be a rectangle. And this is the cross-sectional area for a rectangle. Okay, so you take basically the OD minus the ID divided by 2, multiplied by the height, and that gives you the cross-sectional area, which is given as AE. Okay, so here it is in millimeters squared, here it is in centimeters. So why is that important? Let's take a look at that. What you want to be able to do is to calculate the maximum flux density, and there's an online calculator here that you can find in day counter. I'm just going to tip my camera slightly. You can see the URL on the bottom there. This calculator allows us to calculate the flux density, which we typically call B, in Gauss. And the variables that we need are the RMS voltage, the frequency, the number of turns. Here's where the cross-sectional area comes in, okay, in cubic centimeters. So we said 1.87 based on our calculation. And this is if we had any DC current, which in this case we don't. So it simplifies the calculation. So basically, it's based on Faraday's law. So here's the equation that we use. And again, this online calculator does all these calculations for you. You just have to plug in the number. And the Gauss for our particular application would be around 705. Okay, so we're using Gauss as a unit of measure. The newer standard, the SI standard, uses Teslas, but a lot of the old data sheets still show Gauss. And the only calculation that you really need to do here, you're picking the minimum frequency, the number of turns. We just showed the cross-sectional area. So you need to determine what is my RMS voltage. So, of course, there's a lot of Ohm's law calculations that allow us to do that, but I think the easiest one is the power output. Say your maximum power output times R, which in this case is 50 ohms, and you take the square root, and that's where you would determine the RMS voltage. So this is a handy online calculator to determine the Gauss. Now, why is that important? Well, let's continue, and we'll talk about that a little bit more. So what you want to make sure is that you're operating the transformer, the ferrite cores within their specifications so that you don't saturate the core. So if you look at this particular curve here, I have material 43, material 61, and you see the lower permeability has a shallower slope, so it doesn't rise as fast, and the higher permeability a much steeper slope. So material 43 will saturate before material 61. Now, why is that important? Well, if you look at this other curve, you'll see that when the transformer's in the linear region, okay, when it's below saturation, your waveforms will be less distorted and more linear. But once you reach this knee in the curve, okay, and the core starts to saturate, you can see it changes very quickly and becomes nonlinear. You see that happens quickly, and that will result with nonlinearities and distortion in the output signal. It will also limit the bandwidth of the amplifier, and this produces harmonics and affects the IMD, the intermodulation distortion. So it's important not to saturate the cores when we're operating our RF amplifier. So let's talk a little bit about Orsted's and saturation point in the materials. Okay, you saw in the specification that it specified the B field in Gauss and the H field in Orsted's. Okay, so what are we looking at here? The B field is just the flux density, and the H field would be the field intensity. Okay, so if we do the calculation, this makes it very clear why material 43 saturates at a much lower point. So yes, it has a higher Gauss, and maybe some of you are wondering about that. Well, the Gauss rating, the B is higher, so why does it saturate sooner? And so here's the formula. It's pretty simple. You basically take B divided by the permeability, and it gives you the Orsted's. So we said 2950 divided by 850 is Orsted's of 3.5. So that's a much lower saturation point. It takes a lower current to saturate. Material 61 is considerably higher, even though the permeability is lower. Even though the Gauss rating is lower, right? The permeability is also much lower. So when you do the simple math, B divided by U, permeability, you see you've got 18.8 Orsted. So it has a much higher saturation point. And that's why we use material 61. Okay, and we choose that so it has a high level of AC current and it will not saturate. Now, another standard would be, instead of using Gauss, you could use Tesla's. I see some of the new data sheets using Tesla, and instead of using Arsted's, now they're using amps per meter, A/M. So you might see different terminology there, and if you read that last statement on the bottom there, I just have it footnoted. So that's the newer units of measure that are typically used. But they're the same, and the calculations are all the same. So that's why we use material 61. Okay, you can see that the Arsteds are higher, and therefore the saturation point is higher. Okay, so now we're going to talk about the turns ratio and impedance ratio, which I briefly touched on in the beginning. Basically, we need to know what our load is going to be, and there's a couple of different ways to do this. You could use the output impedance in the data sheet, or a very good approximation is just to take VDD squared divided by 2P. Okay, so for a single LDMOS transistor, BLF188XR, let's say I wanted to operate it at 850. Remember, this is a Gemini package. So there's two transistors in a single package. So each transistor would basically be used for 450 watts of power. So if we take 50 volts as our operating voltage and we square that, we have 2,500. If we take 2P, we have 850, right? 425 times 2. And if we divide that out, we have 2.9 ohms per transistor. But remember, this is a push-pull configuration, so the impedance seen by the transformer itself is basically drain to drain. So we have to multiply that by 2. 2.9 times 2 is 5.8. So that's the total load. So if we look at our different turns ratios now on our transformer, okay, we see that if we need 5.8, we divide 50 by 5.8, and we get 8.6 to 1, okay? So the closest ratio to that would be 9 to 1, which is shown here, okay? And if we take the impedance ratio of 9 and we take the square root, okay, the square root of 9 is 3. So we're looking at a 3 to 1 or 3 turns. Now, you're very limited with this type of transformer technology. Typically, for LDMOS amplifiers, we either use 3 turns or 4 turns. So 3 squared is 9 to 1. 4 squared is 16 to 1. So you're limited in how many different ratios you have with this type of transformer technology. And you have to basically select the closest ratio that's going to give you the best performance, either the best power output or power added efficiency. Typically, we look at both. When you look at the Smith chart, you look at the contours on the Smith chart, you're trying to get good output, but also good efficiency. So there's a trade-off to that. So if we take 3 squared is 9, and if we take 50 ohms as our load, divide by 9, we get 5.6 ohms. Okay, and the perfect match for this particular application would have been 5.8 ohms, so it's very, very close. Okay, so also, there's a minimum amount of inductance that's needed for the primary and the secondary. And the rule is usually 4 times the load. Okay, and that would be on the input side and the output side. So here's the formula, minimum inductance. L equals 4R divided by 2 times pi times F. Okay, so I go through those calculations, and the worst case is going to be the minimum frequency. So if we're looking at the high frequency band, broadband, right, 1.8 to 30, so you have more than a 28 megahertz bandwidth there. Worst case would be the lowest frequency. So we typically design around that. And if we look, remember what we said, the drain-to-drain output impedance for our example is 5.6 ohms. So 4 times 5.6, we would need basically 22.4 ohms, okay? So when you work the equation backwards, that would be a minimum inductance of 1.98 microhenries, which is shown here. And if you work the math back the other way, right, 1.98 of microhenries, okay, and then we just use the formula for inductive reactance, 2 times pi times frequency times inductance, then we would calculate the inductive reactance, XL, as 22.4. So it's just a check to say, okay, that's the minimum inductance. Okay, so when we measure the actual transformer, okay, this design here, okay, I'm getting 2.4 microhenries on the primary. And if I calculate the inductance using this same formula, I get 27 ohms. So we meet the criteria for minimum inductance and minimum reactance or impedance at 2.4 and 27. We can do the same thing on the output side. So again, minimum frequency. This time the load is 50 ohms. So 50 times 4 is 200. So again, if we work through the simple math, we'd need basically a 17.69 microhenries. And if we work that the other way, we see that 17.69 microhenries, okay, if we use the formula 2 times pi times frequency times L, yes, in fact, it is 200 ohms. So that's the minimum. Now we go back and we measure, okay, the actual transformer. I got 21.8 microhenries, so that's above the minimum, and I got 247, again, above the minimum. So this tells us that the transformer design meets this design rule of at least 4 times higher. And that's a good design rule. I've been using it for years. It's published in a lot of textbooks. And here's a reference, okay, AN 749. This is a Motorola application note. And this is also another reference from RF Techniques, Chapter 5. This is a textbook that I use, a very common textbook. And here's all the formulas, and here's the terms that are used in that formula. And it can be used for either bipolar or LD-MOS. You would just look at either for bipolar, instead of gate to gate, it would be base to base. And instead of collector to collector, it would be drain to drain impedance. But other than that, the formulas are all the same. And again, this just shows the basic construction of the transformer that we typically use with the ferrites and the copper tubing and the end plates. And you see here my note, should be 4 times higher as a minimum. Okay, so this next topic, covering that, would be looking at the permeability of the transformer and the leakage inductance and the K value. So this is an important topic. If we see the ideal transformer, right, if I go back and just show the ideal transformer here, bear with me a moment, and I think I'll just scroll down to my LT Spice slide. This is an ideal transformer, right? In the perfect world, right, we just have a primary and secondary, and there's no parasitics at all, okay? But in actuality, when we look at the transformer, there's a lot of parasitic effects. So you have the resistance of the primary winding, you have the leakage inductance of the primary winding, which we're going to spend some time talking about. You have the capacitance of the primary. You have the resistance of the core. Those are core losses. You have the magnetizing inductance, right? And then on the other side, yes, we have capacitance in the secondary. That's just between the wires. and then we have the leakage inductance of the secondary and the resistance of the wire. And then between windings, we have the intra-winding capacitance, the capacitance between the two coils. So the transformer, although it looks like a simple component, actually is a pretty complex component. But there's only a couple of things we really have to worry about. And the primary one is the leakage inductance. So here's the transformer I showed you. The primary was 2.4 microhenries. The secondary is 21.8 microhenries. Okay, and if you use this open short method, you can actually measure the leakage. So if I measure the primary side and I short the secondary side, that gives me the leakage of the primary. And then if I measure the secondary side and I short the primary, that gives me the leakage of the secondary. So this is a very common test that's used to determine the leakage inductance. So here's the numbers that I had from my inductance meter. 0.15 microhenries for the primary, 0.66 for the secondary. And what do? This leakage inductance, it has an effect on our match. And we'll look at that in a little more detail when I get to the SPICE simulations and the following slides. But typically, we will use a tuning capacitor on the primary side and the secondary side, and there is a methodology that you can use to calculate these values and get very close. Of course, the final values would be determined in the circuit because of the circuit board and the parasitics there, but you can get reasonably close. Okay, so we're using basically two capacitors for the tuning and the compensation. Now for LT SPICE, we also need to determine the coefficient for the transformer, the coupling coefficient, how well the primary and secondary are coupled. So here I just looked at the secondary side, and here's the formula. The coefficient coupling is equal to the square root of 1 minus the inductance shorted and the inductance open. So basically square root of 1 minus, here's the leakage inductance for the secondary, here's the inductance measurement for the secondary, and when I go through the math, and it comes out to 0.985. So that's the coupling coefficient that LT SPICE needs to calculate how the transformer will perform. All right, so now we're looking at an LT SPICE simulation of an ideal transformer. This is the transformer that I showed earlier. Here's the primary and secondary inductance, and it's a 9-to-1. But this is the ideal transformer. It does not include all the parasitics that we showed on the previous slide. And you could see after 1 megahertz or so, the response is very flat, okay, all the way beyond 30 megahertz, the high frequency band. But what happens when we model in all those parasitics? Okay, well, you can see the response changes dramatically. We have the resistance of the primary and secondary coils, and then we have the leakage inductance, we have the parasitic capacitances. Okay, so for a practical transformer, you can see that there's a roll-off after about 10 megahertz or so. So we have to compensate for that and compensate for some of the parasitics. And on the high end, where we see most of the loss after 1 megahertz and after 10 megahertz, we basically experience those losses because of the interwinding capacitance and the series leakage inductance. So there is a way to measure that on the NanoVNA. We can do a back-to-back method. I'm going to just move the camera quickly and show the methodology here, and then we'll go back and look at the details. But I have two of my transformers, and you can see on the input side, this is basically the unbalanced side, and then this is the balanced side for the push-pull amplifier. I have those soldered together, and then it goes back to the unbalanced side. So this is a typical measurement method that you can find in a lot of application notes, including Coilcraft. So, as I said, we go from unbalanced to balanced, then balanced to unbalanced, right? And that's our 50 ohm path, okay? And here's the step-by-step procedure. We connect the unbalanced side to port 1, 50 ohms. The intermediate connection of the two balanced sides connected directly together. And then on the output, we take the unbalanced side, 50 ohms, to port 2. Okay, and this is what we need to do with any VNA, okay, since we want to look at the unbalanced signals. And then you would basically have to divide the results by 2, assuming that the two transformers are identical. And this is about as close to identical as you could get from a practical standpoint. And then we divide by 2, as I show there, and we get the insertion loss from the NanoVNA. So here's an example. If we look at this, let me just pull my camera out a little more. There you go. Okay, so this is going from basically unbalanced to unbalanced. So this would be like a single-ended RF amplifier, okay, where we just have our drive signal goes to ground and the output signal also goes to ground. So it's a single-ended, balanced, unbalanced output. Here we have a push-pull amplifier where we have our input signal again, all right, but this time it's balanced on both sides, and there's a 180-degree phase shift here, right? It's a push-pull amplifier, so we're driving the transformer with two signals that are 180 degrees out of phase, and we go from balanced to unbalanced through our transformer. So you have the output of the transformer and then ground, okay? So we're going from balanced to unbalanced, okay? So with the NanoVNA, the back-to-back measurements, we take port 1, it's a 50 ohm port, okay, and we go to the unbalanced side, and then we have the two balanced sides of the transformer connected together, and then the output, okay, which is unbalanced, is connected to port 2, which is also 50 ohms. And we're able to measure the insertion loss through this arrangement, and then because they're identical, we divide by 2, and it gives us the insertion loss of a single transformer. So here's the actual results. If you look at the insertion loss, this is for 2, so you divide by 1. You divide by 2, so it's 2.35 decibels, okay, for each transformer, and this is without tuning. And here, same thing, okay, but this time we add the tuning capacitor, and we see if we divide by 2, it's only a half a dB, which is excellent performance, minimum amount of insertion loss through the transformer. And this is exactly what you're looking for. This is what you're trying to achieve, is to minimize the insertion loss, which is going to maximize the power transfer. And again, we said you can see it rolls off on the high end, right? We saw the same thing with the SPICE simulation, and we see that the high frequency insertion loss is caused again by the interwinding capacitance and the series leakage inductance. So we're going to try to tune out some of that series leakage inductance and see how that helps the performance. Okay, and here's the procedure to calculate the capacitance needed I'm going to hold off on this and set up the actual live measurement, and we'll see how it looks with the tuning capacitor in place and see what improvements are realized, and then we'll go through the methodology on how to calculate it. All right, so here's my setup. Again, I'm using the NanoVNA with the software NanoVNA Saver. And let me just swing the camera over here, and you can see the two transformers set up in a back-to-back configuration, which we already explained. And then the NanoVNA here with the actual measurements. Now, one thing to note, I calibrated with this length of cable, which was fine, but I also made sure that I calibrated using the right reference plane, which is right at the end of this connector where these two screw terminals are. So what I did is I kept the BNC adapters on the end of the cable here, and I added another BNC adapter. So when you line this up, you see that it's right at the screw terminals. So you have to add that extra length in order to ensure that you're getting accurate measurements. So a little bit of care has to be taken there. So there's my setup. There's the NanoVNA. Now we'll go over and look at the software real time. Okay, and we're going to go ahead and sweep this. And I'm getting about -5 dB. So remember, there's two transformers, so you would divide that in half, so it's 2.5, rounded off. So what we have to do here is we have to tune it. So I'm going to add some tuning capacitors. The calculated value, which we're going to go through in a minute, was 750. So I'm just going to add that value across the output transformer the way we would normally tune it. And we'll sweep again. And you see that it went from -5 dB to about -3 dB. And we're getting a little bit of a roll off here at the very end on the high end. Okay, so that's the calculated value, but remember what we said, that there are some parasitics. Okay, even in your test setup, there might be some parasitics, but certainly on the board. So now I'm going to go the next standard value down, which is 680. I'm going to add that across. And we see, some additional improvement, about 1.1 dB. So we divide by 2, gives us 0.55. So very close to my original measurements. If I go back to my PowerPoint slide here, very close to that. And I'll just put this in presentation mode again. So yeah, I came out with 1. I just measured 1.1, rounded off. So you can see that we're able to compensate by just adding a capacitor. I'm using a standard silver mica cap that you see there, and just had a number of values. Obviously, I tested this ahead of time so things would go right during the video. And it appears that 680 is the best optimal value. So again, the only real important thing is the calibration. Make sure that you're calibrating at the reference plane no matter what combination of adapters you're using. This is extremely important. Okay, so here's the method for calculating the capacitor value. Okay, we already talked about RF transformers. They have basically inherent leakage inductance due to the uncoupled inductance, which the transformer and the circuit sees as series inductance. And the tuning capacitor basically acts like a shunt placed in parallel with the primary winding, and what its job is to basically resonate out the leakage inductance. And that's what allows us to tune it to reduce the insertion loss. So we're talking about resonance. So here's the formula. F equals 1 over 2 times pi times the square root of normal formula is L times C. This would be L leakage. In this case, we're looking at the leakage inductance here. And we normally pick the center of the band. Okay, so 30 megahertz, we use 15 megahertz. Here's the leakage that we measured that I went through on my last slide. And again, this is just the formula for resonant frequency substituting to calculate for C. So C would equal 1 divided by 2 times pi, and then times the frequency squared, and then times the capacitance value. So when you go through the math, you're going to get 750 picofarads. And we found that one value less gave us a little bit better results. I have a spreadsheet that does all these calculations, everything I showed here in the video. So if you're interested, just send me an email and I will send you a copy of that spreadsheet. Now, one thing to point out is that the capacitance value for one transformer would be half that value. And if you were using this and tuning it in a circuit, you have to subtract the output capacitance from the total value. So this would be 750 divided by 2, be 325. And then for a BLF 188 transformer, if you go to the data sheet, you look at the output capacitance, COO, it's 212 picofarads. So you'd have to subtract that from the 325 picofarads. So that's going to give you about 112.5 picofarads. And again, there's parasitics. So my tuning ends up to be around 120, so it's very, very close. So that's the formula, just formula for resonance, and you see the method does work reasonably well. Okay, so let's just wrap up here then. We talked about a conventional transformer in this presentation that's used in RF applications, and basically we said we were using material 61, okay? So we talked a lot about that, why material 61 is used. It has a low permeability, which means it will not saturate at low levels of current, takes a much higher amount of current than material 43 or 28. And we calculated what our impedance ratio should be, and then we take the square root of the impedance ratio, and that gives us the turns ratio. So we had 1 turn in the primary, 3 in the secondary, gives us 3-to-1 turns ratio, 9-to-1 impedance ratio. We calculated what the minimum inductance should be, 1.98 microhenries. The measured inductance was 2.4. And that would be on the primary side, and the primary impedance then in ohms, the minimum was 22.4. We came out with 27.1. So we meet that requirement, and then remember it's 4 times the load. Okay, so on the output side, we had basically a minimum inductance of 17.69 microhenries. The measured value was 21.8 microhenries. And when we calculate the inductive reactance in ohms, remember 4R, so 50 times 4 is 200. And we came out with 246. And these are just minimum values that we're trying to achieve. Question might be, well, what happens? What's the maximum value? Generally, there's a lot of latitude here. I'm not going to pretend that I have the answer to that question, but in most cases, with these type of transformers, you're going to be in this range. Leakage On the secondary, 0.66. On the primary, 0.15 microhenries. And we saw an insertion loss of 0.5. That was my original measurement. I came out with 0.55 doing it here live in the video. So this is our conventional transformer. Basically, we're matching the output impedance of the LDMOS transistor, okay, the calculated impedance that we need, which was 5.6 ohms on the primary side to 50 ohms on the secondary side. So we're going from a low impedance to a higher impedance, and we're going basically from balanced to unbalanced. And this just shows you the schematic representation. So that's the presentation. I hope this has cleared up some questions you might have had. And again, if you're interested in the spreadsheet that I have, just send me a quick email. The email address is on my channel. All right, RF Man. Thank you.